Every night, the sky looks calm, predictable. Stars fixed in their ancient places, galaxies quietly drifting billions of years away, the universe behaving exactly as we were told it should. But what if that calm is an illusion? What if the reason the universe feels so orderly from where we stand is not because it is simple, but because we are trapped inside something vast enough to hide its own walls? For centuries, humanity believed Earth was the center of everything. Then we learned we orbit the sun. Then the sun became just one star among hundreds of billions. Then our galaxy became one of trillions. Each time we thought we understood our place, the universe quietly corrected us. Not loudly, not dramatically, just enough to remind us how small our assumptions were. Now a new idea has begun to circulate at the edge of modern cosmology, an idea so unsettling that many scientists hesitate to even phrase it out loud. The possibility that our entire observable universe exists inside a cosmic hole. Not a hole you could fall into, not a sci-fi tunnel or a tear in space, but a structure written into the mathematics of gravity itself, a boundary so large that from the inside it looks like infinite space. If this is true, then everything we think we know about expansion, time, distance, and even the beginning of the universe may be incomplete. Not wrong, just unfinished. And the most disturbing part is not that we might be inside a cosmic hole. It is that, if we are, there may be no obvious way to tell from the inside. If you're drawn to slow, thoughtful journeys through the deepest questions of science, subscribe to The Boring Universe. Like this video if you enjoy long-form cosmic documentaries, leave a comment to support the channel, and tell us which part of the country you're watching from. To understand why the idea of a cosmic hole is even taken seriously, we have to begin with the universe as modern science currently understands it. Not the poetic universe, not the philosophical one, but the measured, calculated universe built from telescopes, equations, and decades of careful observation. Our best description of the cosmos is based on a framework called the Standard Model of Cosmology. At its core is a simple but powerful idea: the universe is expanding. This is not an explosion outward into empty space, but an expansion of space itself. Galaxies are not racing away from a central point. Instead, the distance between galaxies increases everywhere at once. The farther away a galaxy is, the faster it appears to recede. This relationship, known as Hubble's law, is one of the pillars of modern cosmology. This expansion leads naturally to the idea of a beginning. If the universe is expanding today, then in the past it must have been smaller, denser, and hotter. Extrapolate far enough backward, and you arrive at a moment when all matter, energy, space, and time itself were compressed into an unimaginably small state. This is what we call the Big Bang. Not a location in space, but a moment in time, the origin of the universe as we can observe it. For decades, this picture has worked remarkably well. It explains the cosmic microwave background, the faint afterglow of the early universe still visible in every direction. It explains the abundance of light elements like hydrogen and helium. It explains the large-scale structure of galaxies and clusters. It is, by all reasonable standards, an extraordinary success. But science advances not only by what works, but by what doesn't fit perfectly. And when cosmologists began measuring the universe with increasing precision, small cracks began to appear, subtle tensions, tiny discrepancies that refused to disappear. One of the most persistent problems is the expansion rate itself. Different methods of measuring how fast the universe is expanding give different answers. Measurements based on the early universe do not perfectly agree with measurements based on the nearby universe today. This mismatch is known as the Hubble tension. It is not a minor statistical fluke. It has survived years of scrutiny and improved data. Something in our understanding is incomplete. Another mystery lies in the large-scale uniformity of the cosmos. On the largest scales, the universe looks surprisingly smooth. Matter is distributed almost evenly in every direction. Regions separated by vast distances appear to have nearly identical temperatures and properties, even though there should not have been enough time for them to interact or exchange information. This is called the horizon problem, and it has driven decades of theoretical work. To address these issues, physicists introduced concepts like cosmic inflation, dark energy, and dark matter. These ideas are not arbitrary. They are carefully constructed to fit observations, but they also introduce entities we cannot directly detect, invisible forms of energy and matter that dominate the universe's behavior while remaining frustratingly elusive. As these layers of explanation accumulate, some scientists begin to ask a different kind of question. Not how to fix the model, but whether the model itself is framed from the correct perspective. Whether the assumptions baked into our picture of the universe might be subtly biased by where we exist inside it. This is where the idea of a cosmic whole begins to emerge, not as a replacement for the Big Bang, but as a reinterpretation of what we mean by a universe that expands, cools, and evolves over time. In general relativity, gravity is not a force in the traditional sense. It is the curvature of spacetime caused by mass and energy. Massive objects bend spacetime around them, and everything else follows the curved paths that result. This framework allows for structures that are counterintuitive but mathematically consistent. Among them are black holes, regions where spacetime curves so strongly that not even light can escape. But black holes are not the only solutions to Einstein's equations. There are also cosmological solutions that describe expanding universes, contracting regions, and boundaries beyond which information cannot travel. The equations themselves do not care whether a structure is small like a stellar black hole or vast enough to contain entire galaxies. Scale is not a limitation. Only energy density and geometry matter. Some researchers have noticed that the mathematics describing an expanding universe and the mathematics describing the interior of certain types of gravitational holes are surprisingly similar. In both cases, there is a horizon, a boundary beyond which events cannot influence an observer. In a black hole, this is the event horizon. In cosmology, it is the cosmic horizon, the limit of what we can observe due to the finite speed of light and the expansion of space. From the inside, these horizons behave in remarkably analogous ways. They define what is observable. They determine how information flows. They shape the structure of spacetime itself. And crucially, they are not physical walls. They are geometric features of spacetime. This raises a profound possibility. What if the cosmic horizon we observe is not simply a consequence of expansion, but the interior boundary of a much larger gravitational structure? What if our observable universe is analogous to the inside of a cosmic hole embedded in a higher level spacetime that we cannot directly access? This idea does not claim that we live inside a black hole in the popular sense. It does not suggest a singularity waiting somewhere in our future. Instead, it proposes that the universe we experience may be the interior region of a gravitational configuration whose external structure is fundamentally inaccessible to us. From within such a region, expansion would look exactly as it does now. Space would appear to stretch. Distant regions would recede faster than nearby ones. There would be a horizon limiting what we can see. The laws of physics would remain locally consistent. Nothing would obviously feel wrong. This is what makes the idea so unsettling. If we are inside a cosmic hole, the universe would look almost exactly like the universe we already observe. The difference would not be in what we see, but in how we interpret it. Historically, this would not be the first time humanity misunderstood its cosmic context. Before Copernicus, Earth's motion was invisible to everyday experience. Before Einstein, the curvature of space-time was undetectable with ordinary instruments. Each time, the universe behaved in ways that made sense within an incomplete framework, until a deeper theory revealed a hidden structure beneath the surface. The idea of a cosmic whole belongs to this tradition of quiet revolutions. It does not announce itself with spectacular anomalies. It whispers through equations, through mismatches in data, through conceptual discomfort at the edges of accepted models. Importantly, this idea remains speculative. It is not a confirmed theory. It is not the consensus view. It is one of several interpretations being explored by physicists attempting to reconcile gravity, cosmology, and quantum theory. But it is taken seriously enough to be studied, published, and debated in scientific literature. If the universe is the interior of a larger gravitational structure, then the Big Bang might represent not the absolute beginning of everything, but a transition, a boundary condition, a moment when space-time took on the geometry we now inhabit. The question of what came before would not disappear, but it would change form. It would no longer be about time before time, but about geometry beyond our horizon. This perspective also reframes the idea of cosmic expansion. Instead of space expanding into nothing, expansion could be understood as the natural evolution of space-time inside a bounded region. The observed acceleration of expansion, attributed to dark energy, might reflect properties of this geometry rather than a mysterious force filling space. None of this negates the achievements of modern cosmology. The measurements remain valid. The observations remain real. What changes is the story we tell ourselves about what those measurements mean. At this stage, the idea is less about answers and more about humility, about recognizing that even our most successful models are shaped by the limits of observation, that the universe we describe is, by necessity, the universe we can see, and that there may be larger structures, deeper contexts, and hidden boundaries that leave no obvious fingerprints on our local environment. If we are inside a cosmic whole, then the universe is not just vast, it is layered, and our layer may be only one chapter in a much larger cosmic architecture. This possibility does not make the universe feel colder or more mechanical. It does the opposite. It restores a sense of mystery that modern precision sometimes erodes. It reminds us that knowledge does not end when equations balance. It evolves when we dare to question the assumptions beneath them. To move deeper into this idea, we need to talk about horizons. Not the kind you see at the edge of the ocean, but horizons embedded into the fabric of spacetime itself. Invisible boundaries that do not exist as physical walls, yet absolutely determine what can and cannot be known from a given position in the universe. In everyday life, a horizon is just a matter of perspective. If you climb higher, you see farther. But in cosmology and relativity, horizons are not about height or vantage point. They are about causality, about which events can ever influence one another, even in principle. The most familiar example is the event horizon of a black hole. Once something crosses this boundary, it cannot send information back out, not because of a barrier, but because spacetime itself is curved in such a way that all future paths lead inward. From the outside, the horizon appears frozen, eternal, unreachable. From the inside, it is not experienced as a sudden wall at all. Physics continues locally as usual. The laws do not break. The boundary is global, not local. Now consider the observable universe. There is a maximum distance from which light has had time to reach us since the beginning of cosmic expansion. This distance defines the cosmic horizon. Beyond it, galaxies exist, but their light will never arrive here. Not because it is blocked, but because space expands faster than light can cross it. Again, this horizon is not something we can touch. It is a feature of spacetime geometry. What matters is that both horizons serve the same fundamental role. They divide reality into what can be observed and what cannot. They are limits not of existence, but of access. In Einstein's general relativity, the equations that describe black holes and the equations that describe expanding universes come from the same mathematical source. Change the distribution of mass and energy, change the symmetry of spacetime, and the same equations produce radically different interpretations. What looks like a collapsing region from one perspective can look like an expanding universe from another. This is not metaphor, it is mathematics. One of the most striking results of modern theoretical physics is that the interior of certain black hole solutions can be mathematically mapped to cosmological spacetimes. Inside, spacetime behaves like a universe with its own time direction, its own expansion, and its own causal structure. From the inside, the singularity is not a point in space, but a moment in time, a future boundary rather than a location. This alone does not mean we live inside a black hole, but it does demonstrate something crucial. The same equations allow spacetime regions that, from within, look like entire universes. The question then becomes unavoidable. How do we know our universe is not one such region? The usual answer is that black holes form from collapsing stars, while our universe began hot, dense, and expanding everywhere at once. These scenarios feel fundamentally different. But general relativity does not care about feelings. It cares about geometry and energy conditions. Some theoretical models suggest that black holes forming in a higher level universe could give rise to expanding interior regions that, from the inside, resemble Big Bang cosmologies. In these models, the singularity is avoided or softened by quantum effects, and what replaces it is a bounce or transition. A new expanding spacetime emerges on the other side. Again, this is speculative, but it is mathematically consistent with known physics extended into regimes we cannot yet test. If our universe were such an interior region, then the Big Bang would not be the absolute beginning of everything. It would be the earliest moment of time accessible within our spacetime. The geometry before that moment would exist, but not as part of our causal history. It would belong to a different layer of reality. This idea naturally explains why the universe appears homogeneous and isotropic on large scales. Inside a bounded gravitational region, spacetime can rapidly smooth itself out. Differences get stretched away. From the inside, everything looks remarkably uniform, even if the larger structure is not. It also reframes cosmic inflation. Instead of being an added mechanism introduced to fix early universe problems, inflation-like behavior could be an emergent feature of the geometry itself. The rapid expansion would not be a separate phase, but a natural consequence of the spacetime boundary conditions at the beginning of our observable history. The concept of horizons plays a central role here because horizons hide information. They prevent us from seeing the full structure we are embedded in. Just as an observer inside a black hole cannot see the external universe, observers inside a cosmic-scale gravitational region may never see beyond their cosmological horizon. This leads to a deeply uncomfortable realization. The universe we describe is necessarily incomplete, not because our instruments are insufficient, but because spacetime itself limits what can be observed. In classical physics, ignorance is temporary. Given better tools, more time, or greater reach, we can always learn more. In relativistic cosmology, ignorance can be permanent. Some information is not just hidden, it is fundamentally inaccessible. This challenges a long-standing intuition in science, that with enough data, the full picture will eventually reveal itself. Horizons tell us that this may not be true, that some aspects of reality may remain forever beyond confirmation or falsification from within our cosmic domain. Critics of cosmic hole interpretations often point out that these ideas may be unfalsifiable. If we cannot see outside our horizon, how could we ever test what lies beyond it? This is a serious concern. Science depends on testable predictions, but proponents argue that indirect evidence may exist, subtle signatures in the cosmic microwave background, deviations from expected large-scale geometry, relationships between cosmic expansion entropy and horizon thermodynamics, not definitive proof, but clues. One intriguing connection comes from black hole thermodynamics. Black holes are not just gravitational objects. They have temperature entropy and obey laws that closely resemble the laws of thermodynamics. The entropy of a black hole is proportional to the area of its horizon, not its volume. This suggests that information in a gravitational system is encoded on boundaries, not throughout space. Now apply this idea to the universe itself. The observable universe has a horizon with an associated temperature and entropy. This is not philosophical speculation. It is a calculated result of quantum field theory and curved spacetime. The universe, like a black hole, has thermodynamic properties tied to its horizon. This parallel is unsettling. It suggests that horizons are not incidental. They are fundamental, and if both black holes and universes share horizon-based thermodynamics, then perhaps they are not entirely distinct categories of object. Some physicists go further, proposing that spacetime itself emerges from information encoded on horizons. In this view, what we perceive as space and time are secondary phenomena arising from deeper, boundary-based physics. The universe is not a container of things, it is a process defined by information flow. Within such frameworks, the idea of being inside a cosmic hole is not exotic, it is natural. Our universe would be one informational region among potentially many, separated by horizons that prevent direct interaction. This perspective also changes how we think about size. From the inside, the universe may appear infinite or nearly so. But that does not mean it is unbounded. Just as the surface of a sphere can be finite yet without edges, a gravitational region can be finite yet internally expansive. The phrase cosmic hole is therefore misleading if taken literally. It is not an empty void carved out of space. It is a region defined by spacetime curvature, causal structure, and horizon boundaries. A domain with its own internal consistency and physical laws. And from within such a domain, everything feels normal. This normality is perhaps the most disturbing aspect of all. There is no sensation of being enclosed, no directional pull toward an edge, no warning sign written into the sky. The universe behaves exactly as our equations predict it should, because those equations describe the interior geometry correctly. If this interpretation is correct, then the biggest mistake we could make is assuming that the universe we observe is the entire story, that the observable equals the total. History suggests this assumption rarely survives long. We once believed the Milky Way was the entire universe. We once believed time flowed the same everywhere. We once believed space was static and eternal. Each belief felt complete until evidence forced a broader view. The idea that we may live inside a cosmic hole continues this pattern. It does not diminish the universe. It expands it conceptually. It suggests that our cosmos may be part of a larger structure, governed by the same physical laws but inaccessible due to the very geometry that makes our existence possible. In this sense, the universe is not hiding something from us maliciously. It is simply structured in a way that limits perspective. The horizon is not a barrier designed to deceive. It is a consequence of spacetime behaving consistently. As we move forward, the question shifts. Not whether this idea is comforting or unsettling, but whether it helps us make sense of what we observe, whether it offers coherence where current models strain, whether it opens pathways to unifying gravity, quantum mechanics, and cosmology into a single framework. If the universe is the interior of a cosmic-scale gravitational structure, then time itself cannot be taken for granted. In general relativity, time is not a universal background ticking forward identically everywhere. It is woven into spacetime, shaped by motion, energy, and curvature. Inside extreme gravitational geometries, time can behave in ways that feel almost paradoxical. Within black hole interiors, what we normally think of as space and time exchange roles. Directions that once allowed free movement become inevitable futures. Motion toward a boundary becomes unavoidable, not because of force, but because of geometry. This idea sounds abstract, yet it is a precise consequence of Einstein's equations. In a cosmological context, something similar may be happening. The expansion of the universe defines a preferred direction of time, not because time itself demands it, but because the geometry of spacetime evolves asymmetrically. The universe expands, structures form, entropy increases. The arrow of time points in the same direction everywhere we look. This arrow may not be fundamental, it may be emergent. Inside a bounded spacetime region with a horizon, entropy naturally increases toward that horizon. Information spreads, correlations decay, and time acquires a direction not because the laws require it, but because the geometry allows no alternative. The Big Bang in this view is not the beginning of time in an absolute sense. It is the earliest moment defined within our spacetime domain. A boundary condition, not a creation event. Time does not emerge from nothing. It unfolds from geometry. This perspective quietly dissolves some of the deepest puzzles in cosmology. Why time has a direction. Why the universe began in a low entropy state. Why the past feels fixed while the future remains open. These may not be cosmic coincidences, but consequences of existing inside a region where spacetime itself channels causality in one direction. If this is correct, then time is not a river flowing through the universe. It is a feature of the universe's shape. And like the horizon that limits what we can see, it limits what we can remember, predict, and control. The universe does not simply exist in time. Time exists because of the universe we inhabit. If you enjoy slow, thoughtful journeys into the deepest mysteries of space and reality, subscribe to The Boring Universe and stay with us for more long-form science documentaries. Like this video to support the channel, and let us know in the comments which country you're watching from.